Good morning, students. Today, the topic is Euler Circuit. It comes under nonlinear data structures. The main objectives of this video are learning about the basic concepts behind the Euler Circuit with one example and how to solve the problem on Euler circuits. So before going into the topic, first we have to know what is Euler circuit. So Euler circuit is a circuit that uses every edge in a graph with no repeats. It has to cover all the edges, but there should not be any repeated edge. So why it is called as a circuit means it must start and end at the same vertex. So we move with one example. So the below graph has several possible Euler circuits. So for example, assume the starting vertex is A. So as I told, if it is Euler circuit, we have to reach the same vertex again. That is, the ending vertex is also A. So see the path A, D, D, E, E, A, then A, C, C, E, E, F, F, C, C, B, then A. So this is one example of Euler circuit. Similarly, you can get another possible Euler circuit for the same graph also. Okay, that's why we have several possible Euler circuits for the given graph. So A to E, follow the numbers A to E, E to C, C to A to B, B to C, C to F, then F to E, E to D, then D to A. So again, the starting and ending vertex is same, that is A. So we can have several possible Euler circuits for the graph. So we move on to the Euler path. The Euler path is very similar to Euler graph. Okay. It should also cover all the edges in a graph. There should not be any repeated edge. But what is the difference mean? It does not have to return to the starting vertex. That is the main difference between Euler path and Euler circuit. In Euler path, if you start with the node A, you have to end with the node A. Whereas in Euler path, you don't need to return to the same vertex. That is the condition. So we move with one example. So one example for Euler path is C, A, B, D, C, then again B. Okay, we start with the vertex C. We reach with the vertex B. So it covers all the edges. We don't have any repeats. And moreover, the starting vertex and ending vertex is not same. So this is an example for Euler path. So see the diagram in the right hand side. C A, A B, D A B, then B D, D C, then C B. Okay. So all the edges are marked. So we move on to Euler path and circuit theorems. What is the condition for finding out Euler path and Euler circuit means? A graph will contain an Euler path if it contains at most two vertices. Okay, at most two vertices of odd degree. Okay. So that is in the graph. So if in the graph, if we have two vertices of two vertices of odd degree, then the graph will contain Euler path. Similarly, if all the vertices in the graph have even degree, then you can say that a graph will contain Euler circuit. Okay, so once again, I am repeating the condition. A graph will contain an Euler path if we have at most two vertices of odd degree. Similarly, a graph will contain Euler circuit if all the vertices have even degree. We will see with this with one example. Consider the below graph. The vertices A, C have degree 4. So what is degree? The number of edges incident in the vertex. So for the vertex A, we have 4 edges incident on them. So the degree of vertex A is 4. Similarly, for C, we have 4 incident edges. So the degree of C is also 4. Similarly, we are calculating the degree of B. It is 2. And the degree of D is 3. And the degree of E is 1. So what happened? The graph should not contain the vertices of even degree. Okay, that is the graph. In this graph, all the vertices are having different degrees. That is both the odd degree and even degree. Not all the vertices are having the even degree. So you cannot go with Euler path. So we can move with Euler circuit. Okay. So what is the condition for Euler circuit? There should be at most two vertices of odd degree. So see the figure. The degree of D is 3 and the degree of E is 1. So the condition is satisfied. So you can find out Euler circuit for the graph. Okay. So to find out the Euler circuit or Euler path, we can use depth first search traversal algorithm. Okay. So assume this is the given graph. So we are applying a DFS on this. So from starting vertex is A. So A to B, then B to C. Okay. And from C, we don't have any uncovered edges. So again, we come to A through the back edge. We struck at A. So what happened? DFS algorithm searches through the backtracking process and it see the vertices. Is there any vertex which has an untraversed edge or not? So we move with A, but for A, all the edges are traversed edge. So we move with B. For B, only the edge BC is traversed, but BD is not traversed yet. So we choose the vertex B. And we start again the DFS process. Okay, again the DFS process from the vertex B. So what happened? From B, you can reach D. From D, you can reach E. And from E, again, you can reach B through the back edge. So now we have two different paths, A, B, C, A. And the other one is B, D, E, B. So you have to merge these two paths. But while merging, you should not merge the path at the end. You should merge the path at the beginning. Okay, that is the difference. Okay. So for example, like this. B, we start with the vertex A, B, D, E, B. So this is the first path. After that, you can merge the path A, B, C, A. Okay. So this is how we are calculating the Euler circuit or Euler path using the depth first search traversal. So to construct the Euler path, you cannot simply concatenate the vertices in the order in which they were visited. So that is, you cannot merge like this. A, B, C, A, then B, D, EB. So you cannot concatenate like this. This is wrong. Okay. So instead, we begin with constructing the temporary path ABCA. Then we backtrack to B. After getting stuck at A, we have to insert the vertices visited from B in the temporary path. Instead of inserting at the end, we have to insert them after B. Okay, that is, you have to insert in the beginning. So that is, we get path like this. A is the starting vertex. The second path, that is this one. A, B, D, E, B. Okay. So then from B, you can reach C, A. So this is how the depth first search traversal is used for finding out Euler path and Euler circuit. Okay. We move with one more example. Okay. So this is the given graph. So the usual procedure, pick a vertex and perform a depth first traversal. Mark the edges that are traversed and mark if any vertex that is reached and has no remaining untraversed edges. If this does not lead to a circuit, there is no Euler circuit in the graph. Otherwise, pick a vertex with untraversed edge and repeat the first step once again. So this is the procedure. We will see with one example. So this is the given graph. Okay. First you draw the adjacency matrix. That is, from the vertex 1, we have an edges to the vertices 2, 4, 5, 6. And from the vertex 2, we have an edge to 3. Similarly, we have an edge to 1. And from vertex 3, you have an edge to 4. And we have an edge to 2. Like that, you fill the adjacency matrix. Then assume my starting vertex is 1. So from 1, you can reach the vertex 2. So that edge is marked. Okay, that is 1 to 2 is marked. Since it is an undirected edge, 1 to 2 is same as 2 to 1. So 2 to 1 is also marked. Don't forget, we are applying a depth first search traversal. So from 1, we move with the vertex 2, and from 2, your reachable vertex is 3. Okay, so from 1, we move to 2, then 2 to 3. So mark the edge 2 to 3 as well as 3 to 2. So now we are in the third row. For 3, we have only 2 vertices 2 and 4, 2 edges 2 and 4. 2 is already visited, so we don't have any other way. We have to move to the edge 4. That is like this. From vertex 1, I am moving to the edge 2. From 2, I am moving to 3. And from 3, I am moving to 4. So 3 to 4 is marked. Similarly, 4 to 3, it is also marked. Okay. Now we are in the fourth row. Okay. So from the fourth row, you can reach 1, 5, 6. Okay. What happens if you choose with 5? The next vertex is 5. For 5, we have only 2 edges, 5 to 1 and 5 to 4. So both are already visited. Okay, 5 to 1 and 5 to 4. You cannot reach 6. That is, you are striking at the vertex 5. So you should not move that way. From 4, you go with the node 1. Okay. Hope you understand why we didn't choose the node 5. Because if you choose node 5, 1 to 2, 2 to 3, 3 to 4 and from 4 to 5, what happened in the next step from 5, either you can reach the vertex 1 or you can again reach the vertex 4. Okay. So 4 to 5 I am reaching. So 4 to 5 is marked and 5 to 4 is marked. So we have only one remaining edge, 1. So this is the path I am getting if I have chosen the vertex 5. 1, 2, 3, 4, 5, 1. So here the edge 4 to 6 is not covered. So this is not a possible solution. So instead of moving into 5 from 4, you again go back to the node 1. So what happened? Now we get the path 1, 2, 3, 4 and again 1. And we are finding out, is there any edges which are not traversed? Okay, like this. Pick the vertex 1 and I am seeing whether any non-traversed edges are there or not. So I am going with 5. So 1 to 5. So go to the 5th row. From 5, the two edges are there. One is already traversed. We have 4. So 5 to 4 is selected. So mark the path 4 to 5. Similarly 5 to 4. So 1, 5, 4. This is the path. And again I am coming into the vertex 4. That is the 4th row. Is there any untraversed edges there or not? Only 6 is available. So you can traverse 6. So 4 to 6 is marked and 6 to 4 is marked. Okay. So 6 is added and from 6 I can reach the vertex 1. So now we get the path like this. Okay. From the first iteration I obtained the path 1, 2, 3, 4, 1 and by using the second iteration I got the path 1, 5, 4, 6, 1. So don't forget, the insertion takes place at the beginning. So what happened? My path is 1, 5, 4, 6, 1. That is like this. 1, 5, 4, 6, 1. It is inserted at the beginning. And from 1, you can reach 2, 3, 4. Then finally, we conclude at node 1. So the time complexity of this algorithm is order of B plus E. So that's about Euler circuit. So these are some university questions. Okay. And some of the gate questions may be asked in this topic. They may give like this graph and they ask you to find out Euler path and Euler circuit for the given graph. With this, I am concluding my today's class. Thank you.